Okay, the last couple of questions on this practice grade were to do with second order ordinary differential equations. Looking at this first one, I know it's a second order ordinary differential equation because it's got the second differential in it as well as an equal sign. So let's try solving this thing. For this particular one, and in an exam, you'd always be given the general form of the solution, and for this case, we'll find it's a complex root of the form m equals alpha plus or minus beta j. Then the general solution has this form. So all we've got to do is find the values of alpha and beta by forming the auxiliary equation and solving it. Once we've got the general solution, we've got cos of an angle and sine of the angle. So we can also express it slightly differently, because using this general expression here, a sine theta plus b cos theta, where theta is the same angle, can be rewritten as r sine theta plus alpha, some phase difference, where r equals the square root of a squared plus b squared, and alpha, the phase angle, is the inverse tan of b over a. So we're going to use these things in this solution. So if you'd like to have another go at the question in light of this information that you've just been given, see if you can have a go. I'll go through the solution. Okay, so here's the second order differential equation. So forming the auxiliary equation, m squared plus 4m plus 5 equals 0. Using the quadratic equation, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a, we can find the values of m. So m, sorry, in this case, m equals that. This equation does occur on the exam paper for you to use. So putting the values in, minus 4 plus or minus the square root of b squared 16 minus 4 times 1 times 5 is 20 all over 2a. 2 times 1 is 2. Straight away we can see that 16 minus 20 is going to give us a negative number inside the root, so it's a complex solution. So this means we get minus 4 over 2 plus or minus the square root of minus 4 over 2. Minus 2 plus or minus 2j over 2. Because minus 4 can be written as the square root of minus 1, which is j, times the square root of 4, which is 2. So of course this simplifies down to minus 2 plus or minus j. So the general solution has the form alpha plus or minus beta j. So from that we can see that alpha equals minus 2 and beta equals 1. And we can put them into the general solution to get x equals, or q equals in this case, e to the minus 2t a cos t plus b sine t. And that's the general solution for this differential equation. So now, given this general solution, we've got to find a particular solution so we can find the values of a and b, in other words, given some initial conditions, which are that when t equals 0, q equals q, some initial charge q, and the rate of change of charge with time at the start when you turn the circuit on is 0. So the first initial condition is easy enough to use. Just taking this general solution, we can let t equals 0 and find out the value of q. So little q equals big Q. E to the minus 2, 0 is 1, so that's just 1 times a cos 0 plus b sine 0. Well, the sine of 0 is 0, so cos of 0 is 1. So A equals Q. So that's one of the constants found. To find the other constant, though, we need the other initial condition, dq by dt equals 0. So that means we have to take this initial function, general solution here, and differentiate it. And we've got t, the variable, appearing more than once. So we need to use the product rule to do this. So have a go. And the solution follows. dq by dt equals, so if we let in the original function this part equal u and this part equal v, the product rule tells us the differential is the first part u times the differential of the second plus the second part times the differential of the first. So just writing down the solution, this gives us the first part, e to the minus 2t, times the differential of the second, which is going to be cos becomes minus sine, so it's minus a sine t. Sine becomes cos, so b cos t, plus, so that's u dv plus v, which is a cos t plus b sine t times du, which is minus 2 e to the minus 2t. So that's my differential found. When t equals 0, dq dt equals 0. And when you put the value for t equals 0 in, lots of these terms are going to disappear. So see if you can carry on from here and find an expression for dq dt, which equals 0, equals. Again, e to the 0 is 1. Minus a sine t is 0. So that bit's termed. Cos t is 1, so this gives us b. Plus, in the bracket we've got cos t is 1, so that's a. The sine t is 0, so the second term is disappeared, times minus 2. So we have that 0 equals b minus 2a. But we know from the first initial condition that a equals q. So b equals, or 0 equals b minus 2q. So 2q equals b. So we've got the two constants, a and b. So we can now rewrite the particular solution for q. So putting our values of a and b back into this expression at the top. For q, we have the q equals e to the minus 2t brackets a. So a is q cos t plus 2q sine t. And that's our particular solution. We can tidy that up a bit by taking q outside the bracket. So q equals q e to the minus 2t cos t plus 2 sine t. And that would be the particular solution. The last part of this question, though, asks us to write it in the form of a, in this sort of form here, r sine theta plus alpha. So we've got to find out what's a and what's b in here. So b is the coefficient of theta, a is the coefficient of sine. So going back to our solution here. So b is the cosine of the coefficient of the cosine term. So b equals 1 and a equals 2. So a sine beta plus b cos beta equals r sine beta plus alpha. That's what we're after. R is the square root of a squared plus b squared, which is 1 plus 4. So that's the square root of 5. And alpha is 10 to the minus 1 of b over a, which is 10 to the minus 1/2. Which is 0.464. So finally we can write the general solution. Q equals Q times root 5, or root 5Q, e to the minus 2t sine theta plus 0.464. And that would be the general solution, and it's the answer in the text, or on the paper rather.